All right, so in the last lesson, we did projectile motion the clean way. Ball goes up from the ground, comes back down to the ground. Same height start, same height finish. The time going up equals the time coming down. The launch speed equals the landing speed. The launch angle equals the landing angle. Everything mirrors itself across the peak, nice and symmetric. But the exam writers who love the real world give you projectiles launched from cliffs, balls rolling off tables, cannonballs fired from castle walls, and so on. That is, the launch height and the landing height are different, and the moment those two heights stop being equal, the symmetry breaks. Time up no longer equals time down. Landing speed is no longer equal to launch speed. The angles don't mirror anymore. And this is what we call asymmetric launch. But you see, the velocity in horizontal direction is still constant. The vertical motion continues to be uniform acceleration under gravity, and the two axes are still independent. What changes is where you set your origin, what your initial conditions are, and what your final conditions are. The physics? Untouched. So picture this. You're standing on the edge of a cliff. The cliff is, let's say, 20 meters tall. You take a ball and you throw it at some angle theta above the horizontal with some initial speed v0. The ball arcs out, reaches its peak somewhere above the cliff edge, then comes down past the level of the cliff edge and keeps going down until it finally hits the ground 20 meters below where you launched it from. So where do you put your origin in this case? Well, this is the first decision you make in every asymmetric launch problem, and this actually trips up a lot of students. So I suggest pay attention to this because this itself will make the lesson a lot easier for you to understand. Now, you have two reasonable choices. You can put the origin at the launch point, at your hand, at the top of the cliff, or you can put the origin at the landing point, at the ground, 20 meters below. Either works, but you have to pick one and stick with it through the entire problem. Mixing them is the single most common error I see. I'm going to use the launch point as the origin. That's my preference. Why? Because at the launch point, I know everything. I know the position is 0. I know the launch speed, v0. I know the angle, theta. So my initial conditions are clean. And the landing point, the ground below, has a position of negative h, where h is the height of the cliff, and the minus sign matters. The ground is below my origin, so y landing is negative. Some textbooks flip this. They put the origin at the ground and the launch at y equals plus h. That works too. The math comes out the same. Okay, now the equations. Same as always, just two of them, one per axis. Horizontal, constant velocity, x equals v0 cosine theta t. Vertical, uniform acceleration, y equals v0 sine theta t minus 1/2 gt squared. That's it. Those are your two master equations. Notice, these are exactly the same equations as the symmetric case. Nothing has changed in the physics. What changes is the condition you apply to find the time of flight. In the symmetric case, we said y equals 0 at landing because launch and landing heights were equal. Now we say y equals negative h at landing because the ground is h meters below the launch point. So to find total time of flight, set y equal to negative h. Negative h equals v0 sine theta t minus 1/2 gt squared. Rearranging, we get 1/2 gt squared minus v0 sine theta t minus h equals 0. That's a quadratic, so you'll get two roots, one positive, one negative. Take the positive one. That's the flight time. What is the negative root? That is the mathematical solution corresponding to the trajectory extended backward in time, which of course has no physical meaning here. And here's the exam trap, and I want to flag this one hard. Students see this quadratic and panic. They think they've done something wrong because in the symmetric case, the time of flight had a clean, closed-form expression, t equals 2 v0 sine theta over g. And here it doesn't. The asymmetric time of flight gives you a quadratic with no clean form. That is correct. The asymmetric time of flight is supposed to come from a quadratic. Don't panic when you see it. Now, let's do a special case, the horizontal launch. You're back on the cliff, same 20 meters, but this time you don't throw the ball at an angle, you throw it straight horizontally so the launch angle is 0. What does that do to our equations? Let's substitute theta equals 0 and see. Cosine theta equals cosine 0 equals 1. So V0 cosine theta equals V0. That is, the horizontal launch speed is just V0, the full launch speed. And sine theta equals sine 0 equals 0. So V0 sine theta equals 0. This gives the initial vertical velocity as 0. So our two master equations collapse to x equals V0t, y equals negative 1/2 gt squared. That is clean. The horizontal motion is just constant velocity at V0. The vertical motion is just free fall from rest. The ball moves horizontally because of its launch velocity and falls vertically because of gravity, and the two motions are completely independent. This actually is the famous Galileo experiment. Drop one ball from your hand. At the same instant, fire another ball horizontally from the same height. Which one hits the ground first? You of course know the answer, but now you know the reason as well. They tie. They land at exactly the same instant because the vertical motion is identical for both. The horizontal velocity of the second ball doesn't speed up its fall, doesn't slow down its fall, doesn't affect the fall at all. The fall is purely vertical, determined only by gravity and the initial height. The horizontal motion just decides where it lands, not when. So this is the cleanest demonstration of axis independence in all of mechanics, and it's a heavily tested AP concept. If you see a question that says, a ball is rolled off a table at speed v while another is dropped from the same height, which lands first? They land together, always, regardless of the horizontal speed. And finding the time of flight for horizontal launch is super easy. Set y equal to negative h. Negative h equals negative 1/2 gt squared. T equals square root 2h over g. Notice, this depends only on h, not on v0. The horizontal launch speed does not affect the time of flight. It only affects the horizontal range. And horizontal range, r equals v0 times t, equals v0 times square root of 2h over g. So if you want the ball to land further, you throw it faster horizontally or launch from a greater height. Both work independently. Okay, time of flight, range. Those are the easy questions. Now we go up a level. The exam will ask you, what is the velocity of the projectile at some specific point along the trajectory, not at launch, not at landing, somewhere in the middle? To answer this, we need to find Vx and Vy at that instant, then combine them. Horizontal velocity, and this is the simpler part, Vx never changes. There's no horizontal force on the projectile. And of course, we're ignoring air resistance here and considering it 0. So Vx equals V0 cosine theta, always. At launch, at the peak, at landing, anywhere. It's a constant. Vertical velocity, this one changes. Gravity is constantly pulling down on the ball, so Vy is constantly changing. That is, Vy equals V0 sine theta minus g times t. At launch, t equals 0, Vy equals V0 sine theta, positive, going up. At the peak, Vy equals 0. The ball is momentarily neither rising nor falling. After the peak, Vy becomes negative, going down faster and faster. To find the speed at any point, you combine Vx and Vy using the Pythagorean theorem. Magnitude of v equals square root Vx squared plus Vy squared. And the angle of the velocity vector measured from horizontal at any point would be tan of alpha equals magnitude of Vy over Vx. And here's an elegant shortcut. If you want the speed at a specific height, y, without knowing the time, use kinematics on the vertical axis directly. That is, vy squared equals v0 sine theta squared minus 2 times g times y. This is your old friend, the third kinematic equation, applied vertically. It tells you vy at any height y without ever computing t. Combine that with Vx equals V0 cosine theta, which is constant, and you have the full velocity vector at any height. No quadratic, no time variable, just two squared terms and a square root. This trick, using this equation, saves you so much algebra on the exam. In fact, if you add the squares of Vx and Vy and take the root, what you'll get is a simple expression. Magnitude of V squared equals V0 squared minus 2 times G times Y. Now, the final piece is the projectile has flown its arc, it's coming down, and now it's about to hit the ground. Not the ground at launch height, the ground h meters below. What's its landing speed? What's its landing angle? There are two methods, and I'll show you both because the exam tests both. Method 1 here uses energy conservation, which is technically a Unit 4 topic. We'll cover it properly in a later lesson. So if this feels unfamiliar right now, that's normal. I'm showing it to you because once you've seen energy conservation, this becomes the fastest way to find landing speed. So if air resistance is ignored, mechanical energy is conserved. At launch, the projectile has kinetic energy, half times mass times v naught squared, and gravitational potential energy, m times g times h, relative to the ground. At landing, all gravitational PE has converted to KE, so half times mass times v land squared equals half times mass times v naught squared plus m times g times h. Cancel mass, v land equals the square root of v naught squared plus 2 times g times h. Notice the landing speed depends only on the launch speed and the height difference. It does not depend on the launch angle. A ball thrown horizontally at speed v naught from a 20-meter cliff lands at exactly the same speed as a ball thrown straight up at v naught from the same cliff. Same speed at landing. Different velocities, different directions, different Vx and Vy, but the same speed. This is quite a result, and it's tested constantly. The landing speed for an asymmetric launch is angle independent. Memorize that. Now, if the question asks for landing angle, energy conservation isn't enough. Energy gives speed, not direction. So we go back to components. Vx at landing equals v naught times cosine theta, unchanged from launch. Vy at landing, use Vy squared equals v naught sine theta squared minus 2 times g times y, with y equals minus h. Vy squared equals v naught sine theta squared plus 2 times g times h. So, the absolute value of Vy land equals the square root of v naught sine theta squared plus 2 times g times h. The landing angle, measured below the horizontal, tan of alpha land equals the absolute value of Vy land over Vx equals the square root of v naught sine theta squared plus 2 times g times h, divided by v naught cosine theta. And let's just verify the landing speed by combining components. V land squared equals Vx squared plus Vy squared equals V naught squared times cosine theta squared plus V naught squared times sine theta squared plus 2 times g times h equals V naught squared plus 2 times g times h. Same answer as energy conservation. Good. Two methods, same result. That's how you know the physics is consistent. And here's the key intuition, and this is the headline takeaway from this whole lesson. The landing angle is always steeper than the launch angle, always, because Vy at landing is bigger in magnitude than Vy at launch, while Vx is unchanged. Bigger vertical, same horizontal, steeper angle. The projectile comes in steeper than it went out, and that's the asymmetry. In the symmetric case, h equals 0. The landing angle equals the launch angle. The 2gh term vanishes. Vy at landing equals Vy at launch in magnitude, and the angles match. So, here's what I want you to walk away with from this lesson. When the launch and landing heights are different, the symmetry of projectile motion breaks. Time up doesn't equal time down. Landing speed doesn't equal launch speed. Landing angle doesn't equal launch angle. The path is no longer mirror symmetric across the peak. But, and this is the part I want etched in your brain, the underlying physics is unchanged. Horizontal motion is still constant velocity. Vertical motion is still uniform acceleration under gravity. The axes are still independent. What changes is the boundary condition at landing. U landing is no longer 0, it's minus h. Then you have axis independence, which gives you the elegant Galileo result that horizontal launch speed doesn't affect the time of flight. And you have the landing angle is always steeper in sight, which is the conceptual signature of the asymmetric case. So, I suggest you go through the equations one more time, write them on a single sheet of paper, and make sure you can derive each one yourself without reference. Don't just memorize, derive, because that's how you'll spot the trap when the exam writer changes one number on you.